Now in grade 11 pre-calculus, you learned that the number in front, the a value, sometimes made your parabola wider and sometimes made it narrower. Okay? And the 1/2 made it wider, the 2 made it narrower. Now, if you use that language in the past, we're going to crumple it up into a paper ball and throw it away, because technically, these numbers are all outside. Okay? Outside happens and explains things vertically. When we're talking about narrow and wider, we're kind of talking about a horizontal kind of movement, right? So we're gonna get rid of that language a little bit, and this is going to be things called vertical stretches and vertical compressions. Now, vertical things happen and affect your y value. So I'm going to take this point right here that we started with, 2, 4, and I'm going to analyze what happened on the blue graph. On the blue graph, that point, if it's vertical, the x isn't changing, so I'm looking at the same x. I now have 2, 2. Can you see that your y value was multiplied by 1/2? And we have 1/2 out in front of the equation. Isn't that nice? What about the green graph? We have a 2 outside of our equation. And on my green graph, I could go up here, and now if I plugged in 2 for x, I would get 8 for y. And I noticed that my y value was multiplied by 2. In fact, this is true for all the points. 1, 1, now you have 1, 2. And you might have learned in grade 11 that with parabolas you normally went over 1, up 1, and now you're going over 1, up 2, but it's also explained by the multiplication. The purple one and the blue and the black one are just the green one and the blue one flipped down. Because that negative, we've already learned that a negative outside is a vertical reflection. And so that reflected it over the x-axis. So we're very quickly going to look at these graphs together. This is on page 194. And you have some space beside them, so you have space beside them. I'm going to write underneath, but you can write beside them. Okay? The first one, the number is outside. All of these are going to be vertical stretches and compressions. When we multiply by a number bigger than 1, we call it a stretch. So my original graph here is the red one, and they have 1 point labeled. You can label it as well. They have the point 16, 4 labeled. Okay? In the blue graph, that same point is now at 16, 12. What's happened? We multiplied the y coordinate by 3. We would say that the blue graph is a vertical stretch of the red graph. Visually, how stretches work, imagine that the red graph is made out of rubber, but it's glued to the x-axis. So there's just this point here, just this red point right here. Oh, that's not red. There we go. That's the only x-intercept. It's glued. And then I take that red graph and I stretch it away from the x-axis. I could get to the blue graph. That's what a vertical stretch is as a visual. The purple graph would be a vertical compression. That 1/4 in front would change your y coordinate. So now I would have 16, 1, because I would multiply my y coordinate by 1/4. And we get our new graph. Okay? Those are vertical graphs. Outside, vertical. Vertical always affects the y-coordinate. The second set of graphs. Now do you see that your number is inside the function? Everything inside is horizontal. And x's are liars. So we see something, for example, in the green graph you see the 2. Wouldn't you like to multiply by 2? Wouldn't you like this to be a horizontal stretch? But no. You have to multiply by the reciprocal 1 over 2. You have to flip the fraction and then multiply. And it's actually a horizontal compression. Again, they've labeled one point for us here. I'll label it as well. It's this point right here at 4, 2. And on the green graph, the x-coordinates got multiplied by a half. And we get 2, 2. So our x's are liars for left and right. And our x's are liars for multiplication. You see a 2, it is not a stretch. It is a compression by a factor of 1/2. The reasoning is if you're changing your x value, so let's just look at our square root of x. What would you have to plug in to get to? 4. So if I plugged in 4, I would get 2. Now I look at the green graph. What would I have to plug in now to get 2? Because my y is not going to change. I'd have to plug in 2, not 8, right? Like if we multiplied our x value by 2, we think 8, right? But instead it's always the opposite, because now you're thinking, what would I have to plug in to get to? I'd have to plug in a 2, which is causing my x to be multiplied by a half. So we always do the reciprocal. And it's the same thing for moving left and right. It's like, well, now what would you have to plug in to get 0? If you had x plus 3, you'd have to plug in a -3 to get the 0. And that's why it's the opposite direction. Ooh, testing me already, hey? Why is that, Mr. JR? Okay. And then, of course, you could do both. You could multiply your y values and multiply your x values. But we're going to skip through that, and we're going to go to example 1. Some of my videos online, when we had more time, I did longer explanations. So if you want more stuff on there, you can. Here's the graph of y equals f of x. Sketch the graph of y equals -1/4 f of x. Okay? One of the things we're going to start doing, especially because eventually you're going to have like reflections, stretches, and translations all combined. So one of the things that's kind of nice to do at the beginning is to label the things that you see. I see a -1/4 outside of my function. So I'm going to label that I know that both of these things are vertical. I'm going to use V for vertical. Are you okay with that? Make sense? And R for reflection. And then this is going to be a vertical compression. What has to happen? Algebraically, my y coordinates are going to get multiplied by -1/4. And you're going to have to be a little strategic, because there are going to be nice points and not nice points. I will not choose 7, 7 as one of my original points on my red graph to change. Why? Because I don't like multiplying 7 by -1/4. What are some nice numbers that we can multiply by -1/4? That's the mental math we're gonna think about. We have to do this point. That's going to be super important because it's like a key point. That key point is at 0, 0. If you multiply the y-coordinate by -1/4, do you see that 0, 0 will stay the same? As we go, you'll see I'll start doing this kind of work. I'll show my original point. I'll draw an arrow. I'll tell it what I'm doing on that arrow. I'm going to multiply my y-coordinate by -1/4. And then I'm going to write, then on my blue graph, I'd still have 0, 0. Have some of you been doing some thinking? What would be a nice point on the red graph that I could multiply by 1/4? Mental math-wise, nice. 1. I get a fraction though, right? It's a little harder to, can you think of one I can, like, I love fractions, but 4, 4, or 8, 8, okay? 1, 1 is not bad, you can use it, but you'd have a fraction, you'd have to like estimate where it is. But if I used 4, 4, my x is not changing, but I'm multiplying my y-coordinate by a -1/4. Do you see that you would get -1? Okay? And then you'd go onto your graph and you'd label 4, -1. And if I got you to do it on your own, most of you are going to make a mistake. Now that I tell you that, be careful and try to label 4, -1 on your own without making a mistake. Why is it tricky on this graph? Don't say it loud. I hate it when the textbook does this actually, but that's my own pet peeve. Did you label it halfway in between here? The textbook scale is going by 2s? Oh. Right? Some of us made that mistake. It's like, why would they do that to us, right? Come on. There's no need for that. They could have gone by 1s. So be careful. Technically, that's enough for me to draw this side. I might, choose a point from the other side, this one up here, -8, 8. Where is that going to go? Well, x is still going to be -8, but now I'm going to have -2, and that one is going to be right here. There is my new graph. State the domain and range of each function, so I'll do my domain and range in blue. Domain is everything. Range is the y values are less than or equal to 0. I did that one in interval notation. In set notation, sorry. I'll do the other one in interval notation. The other one, domain is everything, so you could also write domain as everything like that. And the range is that the y values are bigger than or equal to 0. In interval notation, we'd say start at 0, include 0, and go all the way to infinity. So I'm going to do this with domain and range. I'm going to switch back and forth to hopefully you get used to both of them that way. Do you recognize the red graph? The red graph, this is in function notation. They could have given us everything. But you might have recognized that this was our absolute value of x. What did we just graph in blue? We just graphed -1/4 absolute value of x. And we recognize that that -1/4 was outside the function, and that would affect the y values. So you could get a question that just says, hey, could you graph this in the blue box? Then you would have to say, I know what the red graph looks like from my pages that I did at the beginning. What color was this one? 7? Was it green? It was green?
Green.
Yeah, the green one. And then, I know what that graph is. Could I change all my y coordinates like this? No problem. Okay? Now, when you're just doing one thing, this work here, you might not have to show. You could have probably just taken points and drawn them on the other graph without showing that. As we get into more complicated things, you might like to show a little bit more of that. Okay? So, just circle question number 3.